Okay, let's get started. 4 o'clock. So we're going to do this. First part will be tests. So I have a copy of the test right there in my bag. Goes to the highest bidder, like always. I will give you, instead of, typically I go through the book and I'm like, study this book, study this chapter. I'm going to just say what topics I saw on the test that I think you should know. As always, first question is going to be symbolic. So make sure you know how to solve a problem symbolically. But as far as topics, so exam topics. They might not be in order like logically, but when I went through the test like 2 or 3 times, I was like, oh, there's this, and I'd like see a question again. Oh, that'd be a good idea. So first one, pendulums. Pendulums. There's another view somewhere. And you don't have to know how to spell it, so that's okay. But what you do need to know is everything else about it. How they work, period of oscillation, energy associated with it, things like that. 2, plotting. This is a huge hint. Plotting oscillations. Know how to do that. Whether it's for springs, whether it's for pendulum, whether it's for orbital mechanics. Jason loves orbital mechanics. More than half your problems have to do with orbital stuff. Well, not necessarily orbital stuff, but space stuff. So, was that my number 3? Yeah, orbital mechanics. So, know your Kepler laws, first, second, and third, and the math behind those. Basically everything in that. If it has to do with space, you can almost guarantee Jason's going to have a question about it. He loves his space stuff. So, 4, angular momentum. So, this is just smaller stuff. Angular momentum and moment of inertia. Now, moment of inertia, I won't say like memorize every single possible moment because you can have your book, you can have notes, but just know what it is, how to use it, equations that have moment of inertia in it, torque and things like that, which is, 6 is springs, then 7 is torque. So some of these relate like 4, 5, and 7, 6, 1, and 2. Orbital can kind of go with oscillations as well. But then finally, I just wanted to put gravity. So that's the last one I'm going to talk about. It's just know and understand gravity. Because there'll be questions that will be testing your knowledge of gravity. If you don't understand the concept, how it behaves, how to get it, like the gravitational force, how you get gravity from that, ma equals gm 1 times m2 over r squared, things like that. So know what gravity is, know where it comes from, know how it changes. That, and then I'm going to tell you exactly how many questions there are, how many points there are. Okay, so the test is divided into 2 sections. There's 1, which has 1, 2, should make that same, 3 and 4, and they have a, let's see, I'll just say 2 parts. So each of these have 2 parts. 2, each one has an A and a B. So that's 8 questions. And then to match that, the second part has 8 multiple choice. Now, most of them are worth 10. So 10, 10, 10, 10, 10, 10, 10. would come out to 80, but not quite. There are slight variations in the distribution. This actually comes out to 68 points instead of 80. So you have 68 points for the first part, so about 2/3 of it will be on your knowledge of like writing and how you can solve things numerically. Well, not numerically, analytically. Then part 2 is how well you can guess, kind of. So this is, as always, 4 for right, -1 for wrong. So you have the chance to get 32. You also have the ability to get -8. But as always, if you get a negative total on the multiple choice, I'll just give you a 0. I'm not gonna, if you get -8, I'm not gonna subtract from here. That's just not fair. So -8 possible for this section only, which brings the lowest to 0 here. So 68 plus 32, total of 100. You can kind of decide where you want to spend time studying, but once again, and this has no correlation. So you see how there's 8 here, and 8, and 8, no correlation. That just happened. Multiple choice might not even necessarily have to do with all this, but I'm fairly confident that if you studied these 8 things, I'm not going to say only these 8 things, but these were things that popped out. If I went over the test again, I might be able to find 1 or 2 other things. These things would be able to help you quite a bit. So that's how many questions. Other than that, are there any questions about the test overall that I could answer? Because there might be questions that I can't answer. Yeah?
So how last Wednesday we had the substitute going over damp harmonic motion, will that be covered at all?
So, no damped. But he does. There is a specific time where he says undamped. So you need to know what undamped is. But damped specifically, I do not recall a problem that says that. Now you have me question it. I can't look at it though, because. But I don't think so. I think you'll be okay if you don't know exactly how to do it. Okay, any other questions? Okay, so let's go to the homework. So that's all the stuff I'll tell you about the test. So this homework is due next Friday. So you'll turn it in with the test next Friday. Okay, so there are 9 problems. I'm gonna go over all 9 of them. I'm gonna give you specific hints for each of them, and whether or not the problem is easy, I may or may not answer a question that you have. Okay, so first problem is actually fairly easy. This is a common theme that you'll see throughout all the homework. So problem 1. Maybe I should have this like last week, how I had like a theme equation. F equals negative G M1 M2 over R12 squared, where R12 is signifying the distance between mass 1 and mass 2. That's all it means. So, gravitational force on one object caused by another object. And typically this is going to be a 1 as well. So it's a force on mass 1 with respect to mass 2 and the distance between them. And it's a negative because it's attractive. So it wants to go the other way, it wants to go towards it. Okay, so problem 1 is really easy. And so all I'm going to do really is draw what it looks like, and then just, that should be able to answer all your questions from A, B, and C. So sun, moon, earth. And this is also a distance. And then you have this distance. So we'll call this R1, R2, R3. By definition, R3 equals R1 plus R2. And question A, part A, asked what force is exerted by the sun on the moon? So what force here is exerted on this force here? Use R1 there, mass 1, mass 2. The force exerted on this from this. Then the next one, what force is exerted by the Earth on the Moon? Earth on the Moon. Use R2. Masses of the Earth and mass of the Moon. What force is exerted by the Sun on the Earth? R3. Mass 1, Earth, mass 2, Sun. Any questions? That's part A, B, and C. Okay. Problem 2. I'm going to erase all this. Problem 2, it has two pictures and then it kind of gets complicated in its explanation, but try to pull out the information that it's trying to ask. This talks about a satellite of Uranus is shown in part of the figure below. It can be modeled as a sphere, blah, 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 blah. So things you want to know, you want to pull out is R equals 2, and this should be the same for everyone, it's not red, 242 kilometers. Okay, so the radius of this sphere that's been modeled, 242. Mass is 6.68 times 10 to the 19th. And the first thing it asks, find the free fall acceleration on its surface. What's the mass of the object falling? Doesn't matter. This is MA, M1A. Get rid of the mass of the object. You're left with the mass of the planet. You already have the acceleration based on that equation. Part B, cliff on Miranda is 5 kilometers high. So this is height equals 5 kilometers. 6 big, it's 5.00. And it says, yeah, this is where it's kind of like just saying stuff that you don't really need to know. But if you're interested, you can look at it and be like, okay, that's where it is. It appears on the limb at the 11 o'clock position in part A of the figure above. Okay, well, let's pull the information out that we need. So some extreme sport guy is on this probably 70 Kelvin planet, just doing his thing. I do not doubt that in the future we'll have like extreme sports guys that go to like different planets and do crazy things. But this guy's there, and the only thing it is he has initial velocity this way, horizontally, which is some velocity initial x. There's no initial y velocity, and it specifically asks for what time interval is he in flight. So that is very simple. No initial velocity in the y direction, meaning that you can use simple kinematics to solve this. If you want to do it, there's multiple ways you can do it. You can do it using kinematic equation, which is a derivation of conservation of energy, or you can just use 1/2 mv squared equals, no, you use, I don't remember this equation off the top of my head, x dang it. That's why I write stuff down. Okay, time equals, oh, because that's for the time. I'm solving the wrong problem. So you use this one. X1 equals x initial plus b initial. So this one, I'm going to write A because it is gravity, but remember that's the gravity on this planet object. So x initial, you can set to 5, you can set to 0, and then that thing, whichever you want to do. But what you really want to do, so no, you don't have to do some crazy thing because this is 0. Solve for t. You get the time. So all it is it's falling with this constant acceleration down 5 kilometers. No initial velocity, solve that. That's your part B. Now part C is, oh man, this one's easy too. I don't know why I thought there's a hard one. Oh, maybe part D. Part D might be the hard one. Okay, so how far from the base of the vertical cliff does he strike? Well, you already have time. So if you throw in times time, you'll know how far he travels horizontally in that amount of time. And because he hits the ground at that point and survives, obviously, because he's extreme sport, this also has to be the same time it takes to travel horizontally. So that's going to be the point at which he hits, is this. X initial, once again, defined, can be 0, bi, which is given, times the time you got, part B. And then part D, this one actually isn't too bad either. Okay, I don't know why, maybe it's a different problem I was thinking of. So you can figure out the velocity when he hits. So he goes way over here. He's going to have some velocity this way, which, if we know, it says, okay, it doesn't say this, but I think you can ignore all sorts of friction and everything because it's in something that doesn't have an atmosphere. This planet's so small it shouldn't have an atmosphere, so no friction. So V final X, V initial X. But then this one, V final Y, you can also get. And it wants to know the total velocity that it's. So hopefully you remember how to solve for the hypotenuse of a triangle. But you have your V final for X, V final for Y, it's a vector. And then you also have to find the angle. And I show problem 3. Problem 3. Okay, this one, I'm not going to convert the units for you, but I'm going to set it up, which is kind of the trick, which some of you might not. If you have an issue with problem 3, it might be because of this. So the question says you have 2 stars, binary stars, same mass, rotating around the middle point, center of mass. Now, there's a couple ways you can do this, but I prefer, let's see, I use conservation of energy, yeah. So I said that there's 2 forms of energy. There's the, did I do that right? No, I did the forces. So I did the force must be equal to each other because they are in a circle. So the circle, the centripetal force must equal the gravitational force because they follow the exact same path. So I said force gravitational equals force centripetal. And the gravitational force we are now gm1 2 over r squared equals mv squared over r. This is either m, doesn't matter, because the main thing that you're looking at is the relationship from one mass to the other. So we pick one mass, it's doing the exact same thing as the other mass. They're both circling the exact same way, so we pick one mass, that is also equal to the other one. But we know that m1 equals m2 anyway, so you're left with gn over r squared equals v squared over r. Now let me see, make sure I know. The question it's asking is find the mass m of each star in units of solar masses. So I need to make sure, oh, this, I gotta be careful because these r's aren't equal to each other. Remember that, so I'm gonna write a d instead. This, if you remember, is the distance between object 1 and 2. It is not the distance between a mass and the center of mass. So this d is going to actually equal 2r. So So it's twice the radius, because if you notice, if you're looking at the picture, it has one mass, this is R, but this is also R. So the distance between the masses is always 2R. As they circle around, it's always 2R. Plug that in, and then you are solving for mass. Now, so 2R, so 4R squared, and then you get d squared. So does it give you, oh, it gives you the period, and it gives you the, okay, so the one thing, I don't know why I didn't write this on this problem. I thought I wrote it. Other thing I should say, V equals R omega. So R is not given, but V and omega are. So you can actually set this problem up in a way that doesn't need R. But you have V and omega, so you can solve for R, plug in V over omega, everywhere there's an R, and you can get the answer. And I got very close to the answer, but with 2 sig figs, I got the exact answer, because there are 2 sig figs in this problem. But yeah, this, that, and that, solve for M, you should get the right answer. Are there any questions for that? Okay. Yeah, that one's a little tricky. But if you just realize that the centripetal force is equal to the gravitational force in that setup, in every circular setup actually, you should be okay. And it's probably important that you understand most of these orbital mechanic ones, because Jason loves these. So just make sure that you understand what it means, what I'm doing. So if you do have any questions, just make sure you raise your hands. Okay, Io, ellipse, moons and Jupiter and Saturn. Io, a satellite of Jupiter, has an orbital period of 1.77 days, orbital radius of, okay, so this is going to be the same answer for everyone. Okay, so orbital radius and orbital period. So it gives you, all right, this is another really important equation, which he showed in class. He showed specifically that if P equals 1 year, A equals 1 AU, then it simplifies it greatly. But for every other situation, you can do this. I guess you could still convert these to years and AU if you want, but for the most part, I stick with everything in standard units. Okay, so you have that equation. It asks for the mass. Gives you the period. In a circular orbit, the semi-major axis is the same as the radius. You have that, you have that, you have that. Solve for M. That's problem 4. Any questions? Kepler's law. This is Kepler's third law. Might be an important one to know. First and second laws, I don't think he'd grill you too much on those. They can be somewhat complicated math. But this one, free game. That's problem 4. Just realize that that's period, that's semi-major axis. If he does ask a question where it's an ellipse and not a circle, know what the semi-major axis is. You need a reminder, semi-major axis is distance from the sun to the furthest point in the orbit. I'm not sure if what he'll do with that, but if he is, that's what it is. If he says something along the lines, I can't remember off the top of my head if he does something like this on the test, but know that this equation is specifically for semi-major axis, not for the radius. It's only, A only equals R if it's a circle. If it's an ellipse, that's what it is. So sun, and then furthest point away, which I don't think you guys even care about the name of it, but it's called apoapsis. Okay. This is problem 5. So problem 5 is about a spaceship being dumb and going straight into a black hole. Yeah, that's awesome. So you have this spaceship 100 meters long. Boom. Cool little spaceship. And so that's 100 meters. This should be the same for everyone. And then you have a black hole that is not to scale. My lines are not to scale, obviously. 10 kilometers. And it is asking, so this black hole is some X amount of times larger mass than the sun. And there's a mass up here, so this is M1, this is M2. Determine the total force on the spacecraft. So this is the equation, but realize that the R, so there's a force here, there's a force here. So this force is the total distance. So the R, so it's the distance from here to this entire thing. So past here. And I checked, if you do not add this 100 meters into the R for your final answer, you will not get correct on by the sign. So make sure your R is 10 kilometers plus 100 meters. If I don't know, it changes like the 100th point, and I was just like, it shouldn't matter. It does matter. So make sure you understand the problem, and the R, the distance, is the distance between this and the very last point of the rocket. Because that's the entire force. Entire force here, here, this is the last point. But then the next question asks, well, what's the difference between the force on the front and the force on the nose and the force on the tail? And so that one just requires you to set this problem up again, except you're looking at the difference. So M1 and M2 are going to be the same. The thing that's different is R, what should I call that? Nose minus R tail. So you want to see the difference in that. So what's the force? So basically all I set this up as is this is force nose minus force tail. I just pulled all these out because those don't change. The only thing that changes is the distance. So one's 1,000 or 10,000 meters, one's 10,000 plus 100. And then you should get a value hopefully much lower than the total amount of force, because this is just the difference in the two. Okay, so that's part, kind of discussed part A, this is part B. Are there any questions on that one? Okay, we're cruising. Everyone just understands everything. Okay, problem 6. So problem 6. At Earth's surface, a projectile is launched straight up at a speed. Okay, this one can be tricky. And the reason it's tricky is because a lot of assumptions that are made cannot be used in this example. And the reason they can't be used is because gravity changes as you go up. And that's what it's looking for here. So you're not just looking for 1/2 mv squared equals mgh, because g is not constant. So the one you want to look for you're looking at the difference in potential energy. So there's a couple different ways to do this. This is the way I did it, and I'll try my best to explain it. So that did not come out right, but I remember it. So typically you would just do G. I'll represent Earth with big M, the object with small m, r squared, R. So this is U. That's potential energy of gravity right here. So I'm saying kinetic energy equals potential energy. So it's the same thing as mgh, except now I'm using a different potential energy equation. This is the same thing as mgh. Just now we have to account for the variation of gravity. The variation comes here with R. Because as you move further away from Earth, you get a different energy associated with it. So the energy you start with, you can actually get further up because you have less force that's pulling you back down as you get further up. So you can actually go further up with that amount. And the way you show it is you look at the difference between the potential energy at the highest point and the potential energy at the launch point. This is U final minus U initial, and I should probably specify that that is negative. Let's see. Potential energy is negative. No. I don't have my book. I know the final look of it, so I'll just do that. So there may or may not be a negative here, just a sec. GM not over anything times 1 over R final minus 1 over R initial, where R initial is the radius of the Earth equals R1. The radius of the Earth plus the extra height equals R2. Oh man, let's call that R2. Oh man, okay, fine. Final, initial, final, okay. I'm doing like 1s and 2s and finals and initials all over the place. Okay, that should be pretty standard now. Okay, so your potential energy here and here. So it is actually negative because you have to flip these in the end. So it should be R initial minus R final to give you an actual positive answer. Because R initial is going to be a smaller value, which means that the fraction is going to be larger. This is going to be a larger value, RF is going to be a larger value, so this fraction is going to be smaller. So if it's smaller minus a larger, you're going to get a negative value. You don't want negative energy. So negative, and just to reaffirm, this is, that's why. Okay, so it's equal to the derivative of the force of gravity over time. So it's equal to the negative derivative of the force of gravity because it's on the bottom and because it's negative. So you have 3 negatives. So you have negative that comes out because of the derivative, and then you have, sorry, that is the integral. You have negative that comes out because of the integral on the bottom. So you have R squared on the bottom, integrate it, get R1, and then negative pops out. 3 negatives. Long story short, you get a negative here. So I'll put it right there. Negative, negative. Then from here, wait, so you plug these in, so you do RE there, R equals H here. This is what you're solving for. So finally, we have what we're solving for. So 1/2 mv squared equals this thing, but you solve for H. So I'm not going to do that for you, but it's now set up where all you have to do is plug everything in if you want, and solve for H. That's it. So you can plug everything here, you can cancel out the m's, plug in the v, move this over, add that over, whatever. You just want to get H. That's your height at which it can go. And this accounts for the change in gravity. So hopefully that makes sense. The reason it accounts for gravity is because it's an integral. So it integrates all the values from the initial to the final. Any questions on that one? Okay. problem 7. Problem 7 is a space probe is fired as a projectile from Earth's surface with an initial speed of something. What will its speed be when it is very far from Earth's? Ignore friction and the rotation of Earth. Okay. So this one is actually in the book. I don't have my book. It's in there. But there's an equation in the book in the 13.6 maybe. I might be. But the equation, I'll tell you what the equation looks like exactly. Well, exactly to what I wrote down. Hopefully I wrote it down correctly. Yeah. Okay, so initial minus R initials squared is energies. They're energies, so they don't have a square. Equals 1/2 mv final squared minus g mm over r final squared. So this is an equation in your book. It's basically conservation of energy, looking at total mechanical energy. Yeah, did you have a question?
Is the R minus supposed to be squared?
No. Oh, nope. Good catch. So energy doesn't have r squared on the bottom because you integrate it, it goes away. Good job. Okay, so total mechanical initial energy, total mechanical final energy, they have to be equal. Conservation energy, they have to be. So the one thing that we can do right off the bat, all of them have little n's. You can just get rid of all of those, which makes sense. Mass just never matters unless it's influencing the other mass. So if you have this ginormous mass, of course it's going to influence it because you have to now look at it from 2 different perspectives. But the initial squared minus gm, we'll look that up. G big M over R initial equals 1/2 v final squared minus gm over R final. So a few tips for this one. So the only thing you're looking for this, so that you have this space probe that's got launched up. It's going really far away from Earth. What is its final velocity once it's no longer being influenced by Earth? So what that means, that this value right here is going to infinity. We just assume that it's going so far away that there's no more influence. And if this goes to infinity, this whole value goes to 0. Nothing. So that's no longer a value. You don't have to worry about that. This is the assumption made for as something goes far away. Now, if there's some sort of question where it's like, if it goes to this point, and it gives you an actual value for RF, then you can plug that in, you can still get the answer. But the assumption made is it's going so far away, as it goes to infinity, what happens? This is what happens. No more influence from the planet, which makes sense. If you're so far away, you don't feel anything else from the planet. So now we're left with 3 terms. 1, 2, 3. We are given the initial velocity. We need to find the final velocity. So what are the values we need? R initial, V initial, V final. So V initial is given. That's given. That we know, mass of Earth. This is mass of Earth. Ri. Let's see if the problem is stated where it was launched from. So probe is fired as a projectile from Earth's surface. So this is Re, radius of Earth. So given, solve for BF. And then you get your velocity. Let's make sure I did that right. Yep, that should come out to the answer. So just solve for that one. And plug in everything else in that you know, you should be able to get it. Any questions? Okay. Problem 8. Problem 8 is, what is the minimum speed relative to the sun necessary for a spacecraft to escape the solar system if it starts at the Earth's orbit? Now this could be a trick question. You have the equation for it, it's given in your book, I'll write it down. V escape equals square root of, okay, 2gm over r. 2gm over r. Well, the escape velocity of the solar system, it says solar system, right? Yeah, solar system, is dependent on the total mass of the solar system. Now, the assumption made here is that the sun is the mass of the solar system. And that's a pretty good assumption. It's like 99.99. I don't think Jupiter comes into play until like the 1,000th decimal place. It's 1,000th the mass of the sun. So it's 99 point, that made like 9 something, I don't know the exact, but we can assume that the mass of the solar system is the mass of the sun. It's called one solar mass. That's a really good assumption to make. Now R might be tricky. So you have 2g mass of sun. So the terminology, I don't remember if Jason writes this or not, but mass, solar mass is denoted with a circle and a dot. Is that right? I think so. And then your radius. Still don't know what your radius is. I will give you a hint, it's not the radius of the sun. It is the radius you start out at when you launch the rocket. We already know what that is. That is 1 AU. You'll have to convert that to meters. But you are launching it from the Earth, so the escape velocity is going to be different if you were launching it from the surface of the sun, obviously. It's going to require a lot more velocity to escape that much closer to the sun than it will be to escape if you launch it from Earth. So you plug those numbers in. Make sure I did that right. Yeah. Just remember that's launching from the Earth, not the surface of the sun. You should be able to get the escape velocity correctly. That's A. Now B is Voyager 1 achieved a maximum speed of 125,000 kilometers per hour on its way to photograph Jupiter. Beyond what distance from the sun is this speed sufficient to escape the solar system? So it gives you a velocity, and it asks you what distance is that velocity viable. Boom. Just change the escape velocity. So this is still your escape velocity. So it's asking, if I was going this fast, how close to the sun could I be and still escape from it? And so you just use the velocity, the escape velocity equation to reverse solve and see where would I be that I could still leave. And it turns out to be way past, or way, and so it was at Jupiter, which is 5.2 AU. This turns out to be an answer less than that. So it was more than okay at that point. So it's Voyager's gone. Okay, so that's 8. Are there any questions on 8? So we got part A, which shows the escape velocity. Remember to use the right R. And we have B, which shows the position with the specific escape velocity. Okay, so 9, like always, I'm just going to give you hints. I'm not going to solve it, but these hints will be fairly, they should help you. That's what I'll say about that. Okay, so you are given the period for which, the minimum period that something can circle a planet with uniform density. And it has to be R independent. It's dependent on the density, so that's an important thing. But it is not dependent on R. So the way we can do this, we use this magical Kepler's third law. P squared equals A cubed 4 pi squared over G. All right. Yeah. Now, it needs to be dependent on density, not mass. But there is a relationship between mass and density. So density, that's a rho, kilograms per meter cubed. So if you times rho by a volume, so you times this by a volume, you get the mass of the object. So our mass is going to equal rho v, where the volume of a sphere is 4/3 pi r cubed. Now, this is your distance away. So this is your r of the planet, of whatever surface you're flying over. A is going to be, we're going to assume circular orbit. I don't know if it says that or not. But we will assume circular orbit because we can do whatever we want. We're gods. We want to find the minimum period, and we can do whatever we want to get to this. So A is going to equal r plus h, so some height. So it's the r of the planet plus height above that. Now there are several ways to solve this problem from here. And I'll try to point you in the right direction. The one way you can solve it is you can say, okay, take the derivative of the period with respect to time and see, the period with respect to height, and see where that is minimized. Because you want to find the minimum time, minimum period for a specific orbit. So you can do that. So dp over dh. So just to be clear, in astrophysics they use p for period. This is also equal to t, same exact thing, it's the period, but they use p. So dp dh, and you want to set that equal to 0, solve for h, find the value that it gives you, and plug that in here. Or you can just realize that the lowest possible orbit you can have in any world is where h is equal to 0. You physically can't orbit inside the planet, but you can technically orbit at the surface, if given a certain velocity. You could. So if we set that equal to 0, you should be able to solve for period, and it will show you that. Man, I gave you way too much. But just know that this is also equal to t. So the problem shows t min equals square root of 3 pi over. That is also p min. T min. So this would be an example of p min, which equals t. Okay, are there any questions on that? I don't know how much I'd be willing to give you anyway, but wow, I don't think there's like 1 or 2 questions in the entire recitation. Okay, well, any other questions? Tests? Anything? Yeah.
Which chapter is the test?
I know it's over 13, I think 15. I can double check.
13.
Yeah, I think that's right. Where are you? There you are. So 11, 15, 13, yeah. So those are the 3 chapters. Any other questions? Okay, well, thank you for coming. Good luck on your tests, all finals. And I will see you next Friday as I loom over you. Make sure you don't cheat.